Hey everybody, this is Michael here from Systems of Human Performance. What I want to do today is go over one of my favorite books on systems thinking. Now, if you Google books on systems thinking, you're likely going to find different books that talk about systems thinking as the subject matter. Things like Peter Seng's Fifth Discipline, things like Donella Meadows' Thinking in Systems. But what I like to do is I like to go and find books that apply systems thinking, that use systems thinking in their argumentation. And what that does is it provides a lot more case examples of systems thinking used in industry and in life, which I find, at least that's how, kind of my mind works and how I learn, is that provides a lot more meat on the bone than kind of some of these theoretical ideas about feedback diagrams and things like that you might find in some of those other texts that have systems thinking as the subject matter. So one of my favorite books that deal with systems thinking is this book from the 1960s. It was written by Ralph Nader. Yes, that Ralph Nader. This is actually the book that kind of propelled him into his political career, and it's called Unsafe at Any Speed. Ralph Nader is a well-known activist of kind of consumer rights, and at the time, in the early 1960s, he had the American automobile industry in his crosshairs. And this book does a very, very good job of using the concepts of systems thinking to support Ralph Nader's argumentation. The most famous example of what he was talking about in this book is the Corvair, which he kind of shows pretty explicitly in chapter 1 how it was not the result of bad drivers, but it was just several design defects in the automobile that was causing all kinds of unsafe behavior of the automobile, and of course accidents, fatalities, things like that. So what I'd like to do is I'd like to go through this book and just kind of, I've highlighted some things and I'd like to share with you why I think they're good examples of systems thinking, or just kind of comment on his argumentation, his thoughts. But also, I think this book does a good job of showing what systems thinking is up against, particularly this argumentation of, it's always the behavior of the operator. It's always the driver's fault. It's never the machine itself. It's certainly not the design of the machine. And that was very much alive in the 1960s as it is today. And we'll see some of this sorts of stuff in this book. So let's just kind of dive into it. I'm starting here on chapter number 2. Chapter number 2 does a good job of talking about kind of a lot of the design flaws of the automobile in the 1960s. I'll argue later that I think I see a lot of these design flaws today. And it also does a good job of kind of pitting this this operator, they were the active reason that the car went off the road or something, so therefore they're the cause, right? So it kind of pits these two ideas. Nader's more of the nuanced systems thinking view, and a lot of the automobile industry's judges, police officers are going to take more of the reckless driver view. So picking up here at chapter 2, I'll read some of these things and then I'll stop to comment along the way. The American automobile is produced exclusively to the standards with which the manufacturer decides to establish. It comes into the marketplace unchecked. When a car becomes involved in an accident, the entire investigatory, enforcement, and claims apparatus that makes up the post-accident response looks almost invariably to driver failure as the cause. To driver failure, right? The active failure. Blame the operator. The need to clear the highways rapidly after collisions contributes further to burying the vehicle's role. Should vehicle failure be obvious in some accidents, responsibility is seen in terms of inadequate maintenance by the motorist. So right there we have our familiar juxtaposition. Is it the design, is it the system, or is it the operator? And Nader even takes it a step farther and he says, sometimes even if we can find that the automobile is to blame, we still try to find a way to blame the operator. We say they didn't maintain the cars correctly. We didn't have the correct air pressure. We didn't, rotate the tires or change the oil enough. So right there, to start off chapter 2, he is putting this 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 duel between the active forces of operator error and kind of those latent factors of design on full display. Nader goes on, I'm going to just kind of skip ahead, but he's talking specifically about there are some braking issues on Buicks in the 1960s. And this got into court cases, and it was determined, in the discovery that, hey, it was the cause of the O-ring failure of these brakes. And the O-ring failure, of course, meant that the brake fluid would drip out of the reservoir. No brake fluid means that when you push down on the brakes, there's nothing to send that energy and push in the brakes on the brake pads that will stop the tires from rotating. So this was all known to kind of the judge, and in the ruling of this person, Wentworth, and whether or not he was responsible for a collision with someone else named Comstock, or whether General Motors, because of their bad design, was responsible, it was thought that Mr. Wentworth's action of driving the car without brakes into Comstock's leg was a new and independent proximate cause of the injury, which superseded the negligence of General Motors. So here we have it, even though, and this is, again, like just kind of to show you the force of that active error, of that blame the operator mentality, is even though the courts knew that General Motors had manufactured their vehicle incorrectly, had designed it incorrectly, they still said, yeah, but it was the guy going out there who was driving without brakes that was at fault. He was the really negligent one. Even though they showed in the discovery that these brakes can actually fail without warning. So the driver might not have even known that he was out there driving around without brakes until it was too late. Looking forward, the record shows that Friend took good care of his automobile. Prompt warning to him would in all likelihood have meant repair before any brake failure occurred. Prompt warning could have easily prevented this accident. So there was another accident, same thing, Buick, brake failures. And what they're actually showing now is, okay, maybe it's not just the operator, maybe it's not just the manufacturer, but it's the whole system apparatus of when failures happen, when things go wrong, we can actually warn people to go and get the maintenance that is required for their vehicles. So that was an interesting kind of development in bringing together systems thinking in vehicle safety, right? If we look at where we are in the 21st century, vehicle safety has gotten a lot better, and the automobile manufacturers certainly take a more systems thinking approach to safety than we're seeing here in the 1960s. And this is just kind of one small step in that direction, where we're not just having that juxtaposition of operator versus machine, but now there's responsibilities of maintenance and of warning and of notification on behalf of the automobile companies. I'm going to pick it up here a little bit later and jump around, but one of the key things here to take away in some of these thoughts is the idea of the latent failures that are built into everything we produce, not just automobiles, but this is one of the key ideas that I bring into systems of human performance and also into all of my discussions of systems thinking, is anything that is designed are going to have latent failures, latent possibilities for error. This comes from James Reason. He's written a whole bunch about this. And the idea is that they kind of act as a virus within the system. The more, not any one latent failure might cause an issue, but the more that are in the system, the more likely it is that something will fail. So let's read what Nader has to say. The fact that automobiles are produced with faulty features or components is commonplace knowledge to those working in industry. Although he tried later to qualify his statement in an interview with the Wall Street Journal, Ralph Mason, manufacturing manager of the Chevrolet division, stated unequivocally in a written message to Chevrolet plant managers, "I am deeply concerned about the quality we are building in our cars today." Later on, each car is tested for a few thousand miles at most. The most latent defects, such as early metal fatigue of suspension arms or rusting through of hydraulic lines, that would appear on cars driven by ordinary motorists are not likely to show up and be recorded for the public safety information. Highly persuasive evidence leading to settlements or verdicts against car makers have involved new cars with headlight failures, leakage of gasoline fumes causing an explosion, a dangerously positioned petcock leaking to brake failure on a bus, stuck accelerators, hood latch defects, allowing the hood to rear up and slam back into the windshield, defectively designed brakes and steering wheels, door latches, and hook hinge failures. So, what Nader's getting at here is kind of two things, right? Is there are two issues that the automobile companies are aware of. One is that they are designing cars poorly, that they are creating latent failures in these designs. And the other is that they're manufacturing poorly, right? That was what the Ralph Mason manager was saying, right? Is that, hey, I'm worried that we're not producing to the specifications that the cars are designed for. We see later on what Nader is saying as well is a lot of this testing, we can't even be aware of these latent failures in the design because we haven't tested them rigorously enough. We're testing them for the first 5,000, 7,000 miles and no more. But we know that the life cycle, even back then, even back in the 1960s, right, means that people are going to be driving these vehicles to 40, 60, 70, 80,000 miles. And that it's absolutely impossible to see those kind of latent errors in the design, such as, rusting through of hydraulic lines or early metal fatigue of suspension arms. It's impossible to identify those things because we're not testing them rigorously enough. And then he goes on to list a whole litany of these things that have actually been found to be design defects in manufactured vehicles. Nader later goes on to talk, I think, in a good way of kind of looking at the root cause, another great systems thinking concept of some of these issues, right? If it's a design defect, if the engineers in the front office designed the car poorly, we're going to see those defects on every single vehicle that was produced, right? Because we're producing to the specification, and the specification is flawed. If instead it's a construction defect and it arises out of poor production and assembly, that points to vehicles that were assembled incorrectly, and then maybe some corrective action is put in the manufacturing line. It's far more likely that the auto manufacturers are going to cop to the manufacturing errors because it's not as systemic, right? It's, hey, there was this error in manufacturing, we fixed it, and now all your cars are fixed. It's less likely that the manufacturers are going to say, our top engineers designed the car poorly, and our top managers did not identify the design flaw, and then we put an unsafe car into the design. We designed an unsafe car and then put it on the road and manufactured it that way. So that's kind of what he goes on to say. Later on, he says the 1953 Roadmaster case, the Ford suspension arm, and the Chrysler steering wheel bracket are evidence of breakdown in production quality control. Even more insidious are hazards that are the products of design. That's exactly what I'm talking about. Born of deliberate knowledge from the engineers, these hazards are far less likely to be admitted by car makers when they are confronted with substantial evidence of their danger. And of course, motorists are not warned of the hazards in owners' manuals. The connection between design defects and driver misjudgment or uncontrollable vehicle behavior is so subtle that neither the accident investigator nor the operator is aware of the connection in the collision. With more and more vehicles employing automatic transitions, the occurrence of the engine-powered runaway accident is rising alarmingly. These accidents display a similar pattern. A vehicle starting from a standstill or a very low speed careens or lurches completely out of control with startling unexpectancy. So here he lists kind of three examples, one from the Roadmaster case, one from Ford suspension arms, and another from a steering wheel bracket. And what he's getting at again is exactly what we were talking about, right? Is that we are more likely to admit that there was an assembly error, there was a manufacturing error, and less likely to admit that the design of the product itself was flawed. That's a much it's a much scarier proposition to commit to. And he kind of goes on, he's going to start to get into this idea of human factors, but if we start changing the designs systemically, we're going to start to see systemic issues, and they're all going to pervade in a similar way. And he gives one example here of the engine-powered runaway accident, right? So now they've switched over in the 1960s to automatic transmissions, and as a result, these engine-powered vehicles, right? You know how when you're in drive, your vehicle just kind of starts to lunge forward a little bit, is going to drive the vehicle into many different objects, people, other vehicles. I'm going to pick it up on the next page, and this is where I think it gets really interesting in terms of what I write about on the Substack, about human engineering, about human-machine interaction, and the way we design systems to prevent and eliminate errors. They occur because of negligent design of the automatic transmission shift patterns. That's just what we were talking about. The driver is charged with reckless driving or negligent manslaughter. Rarely does the police officer recognize that the accident he is investigating proceeded from a built-in design hazard that materialized. In many instances, these driver errors are the result of confusion over the bewildering variety of automatic shifting devices offered in different makes and models of automobiles. And I'll even say for my experiences here in the 21st century, we still have those issues, right? There's all kinds. If you get into the driver's seat of a Hyundai, you're driving a totally different car than if you were getting into a Lexus or a BMW. The controls are very different. The gear shift is different. The way you operate, the headlights and the windshield wipers are very different. And all of that means is that if you step into different vehicles, you have less experience operating that vehicle configuration, and that's going to lead inevitably to more safety hazards, right? Somebody's going to be distracted trying to figure out how to operate the vehicle that they're not going to be paying attention to the road. That's just that's human engineering 101, right? Is that we're going to make mistakes, and the idea of good design is that we try to build consistency and standardization to remove as much of the defects that could occur from those mistakes. Later on, Harvard's professor Ross McFarland says, if defects are present, it is only a matter of time before some driver fails and has an accident. Human engineering tries to identify in advance of manufacture difficulties in the interaction of man and automobile. We usually say man and machine, so as to permit the safest and most efficient operation of the vehicle by the driver. But it takes no science and little foresight to accurately condemn a particularly dangerous transmission shift pattern, the PNDLR gear quadrant, common to Cadillacs, Buicks, Oldsmobiles, Pontiacs, Studebakers, and Ramblers over the past 10 years. This pattern places the reverse and forward low positions next to each other without separation and frequently with such a slight angular difference that it cannot be detected by feel at the knob of the lever. The driver is forced to look at the shift lever for confirmation of the gear in use. The driver has to lift the lever to go into reverse. Should he not lift it enough, the car will remain in forward low while the driver is looking backward and expecting the car to move in that direction. So again, this is just a highlight. Kind of one of the best things about this book that I like is it's a case example of the things we talk about, right? It's human engineering. It's designing systems such that they cannot fail even when the human does. And then he goes on and kind of also to anticipate failures and to avoid bad configurations that can lead to failures. And then he goes on to one such case example of a very particular design decision that leads to failure many, many times, right? It's this configuration of the gear shift box. It goes from park to neutral to drive to low gear and then reverse. And what he's saying is there's no separation between reverse and low gear from going forward versus going backward. And he's saying that's going to cause an error. It's only a matter of time before someone mishandles the knob ever so slightly, and because they're right next to each other, that's going to cause an error, an issue, a collision. What's the better way to do it? Well, it's how we do it now, right? Is you go to park, and then from park it goes to what? It goes to reverse, and then neutral. So going backwards in your vehicle on your gear shift box is surrounded by standstill, either in the neutral position or the parking position. And then only when you go through the neutral position do you get to be going forward into drive and then into low gear. So just by shifting the configuration, the sequence of the gear shift box, we're actually saving lives. We're avoiding collisions. We know that the humans are going to fail, and sometimes they're going to accidentally put it, in park or in neutral. But we know that that's not going to have the same consequence as if they accidentally put it into drive. Nader goes on in a couple pages ahead to just start listing out all of these issues that he's found with human factors, human engineering facets within current manufacturers. And he talks a lot about kind of the visual aspects of it: distortions, waves, ghost images, and poor surface polish on windshields, windshield wiper blades and defrosters, which do not provide an adequate clear windshield area, rear view mirrors with waves and irregularities, windshield wiper assemblies, and other chromium. He was really against chrome because it was so flashy back in the 1950s and 1960s. Many automobiles which persist in using glossy and light colors on the dashboard below the windshield, front and rear turn signals, tail lights, and brake lights not always visible through a full 180 degrees. So this is, you could take all of these things and go out to the cars that are coming off the assembly lines today and find many of the same things. Just because it's 70 years in the future does not mean we've learned from these. If you've ever been behind like a vehicle that has a weird turn signal and you're trying to figure out what's going on with it, if you get into a car and it's configured differently and you're looking around for how to turn on the headlights or the windshield wipers, one of the things that I've always talked about is going back to the 1950s, we've had what's called heads-up display technology, where we could actually display things like the odometer and the speedometer on the dashboard, on the window itself, with kind of like light projection. And we don't do it, and I'm not sure why, but that's going to be much safer. If we don't have to keep averting our eyes to look at our dials on the dashboard, we could always be looking at the road in front of us. Little small design decisions like this is exactly what human engineering, human factors, systems thinking is all about, is how can we engineer and design our most complex systems, and indeed automobiles are one of the most complex systems any of us ever face. How can we engineer those things to prevent errors from occurring in the first place? Even when the human fails, how can we make it so that they fail less often, and that when they do, the impact is much less? Nader in the early 1960s is giving us lots of ideas that I think are still applicable and relevant today. He even goes on in the next page to talk about tinted windshields, which you can, 1 in 10 cars in my neighborhood are going to have, really, really tinted windows that, again, it's not a safety thing, right? Is obstructing your vision, and it's preventing you from driving safe. He goes on to talk about McFarlane, who was that human engineering professor at Harvard, talking about all of the human engineering analysis that they've done on cars and trucks since the 1950s. And it's produced highly usable data on existing vehicle designs in terms of the operational requirements of the driver and his seating comfort. They have also provided standards and criteria for improvements in the design and location of steering wheels, controls, instruments, and workspace for virtually all drivers, no matter what their size. So this is exactly what we're all about, right? Is systems improvement, is finding where the failures are likely to occur, and then figuring out solutions that are going to encapsulate the entire population of operators. What we find, as he continues on here, is that there's all these different kind of configurations, particularly in commercial trucks and buses, but also in passenger vehicles, that are designed in such a way to make it very, very difficult for the driver to operate the vehicle. And the whole contention of McFarlane, who's the Harvard professor, as well as Nader, is that we can design safety into our vehicles. And it's not just preventative safety like airbags and turn signals and seat belts, but it's also things like the interface and the interactions between the humans and the vehicle themselves. And I would contend that, one, that's really good systems thinking. That's kind of, in a nutshell, what we like to talk about as systems of human performance. And also that those are much better high leverage actions, right? If we can design systems so that we're safer to drive, and we have less collisions, that means we don't have to worry about mitigating the impact of the collisions later on through things like airbags and seatbelts, right? So, in a nutshell, that's pretty much what I wanted to talk about in this book, at least in the second chapter. I might at another time do another video going over a different chapter in the book, but for now, I think we're coming up on time here, and I think this was a good analysis of Unsafe at Any Speed by Ralph Nader. I think it does a good job of highlighting some of the systems thinking concepts that I like to talk about, namely things like latent errors, design defects, and human-machine interactions. So if you're interested in this kind of thing, where we're not just looking at the literature of systems thinking, and where we're just talking about books that talk about systems thinking, but actually wanting to see systems thinking applied in the real world, and also see the juxtaposition of kind of what it looks like when people aren't using systems thinking, I think this book, and in particular chapter 2, is a great place to start. So thanks for listening and watching, and please like and subscribe.